the SAS side-angle side Similarity Criterion. Welcome, everyone. Today we are going to explore a very important concept in geometry, the SAS, or side-angle side Similarity Criterion. Now, before we dive into the new material, let's take a moment to reflect on what you already know. In your previous grades, you spent a lot of time studying the SAS congruency rule. You might remember that when we talk about congruency, we are looking for triangles that are essentially carbon copies of each other. They are identical in both their shape and their size. However, today we are shifting our focus from congruency to similarity. This is a subtle but crucial distinction. While congruency requires everything to be equal, similarity focuses primarily on the shape. When two triangles are similar, they have the exact same shape, but they don't necessarily have to be the same size. One might be a scaled-up or scaled-down version of the other. As we move through this lesson, you'll see that the SAS Similarity Criterion is a powerful mathematical tool. It allows us to mathematically prove that two triangles are similar by checking just three specific pieces of information: two sides and the angle trapped right between them. In the next slide, we will look at the formal theorem that defines exactly how this works. Understanding Theorem 6.5. Now that we've established the difference between congruency and similarity, let's dive into the actual rule we use to prove it. This is known as Theorem 6.5. The theorem tells us that we don't need to check every single side and every single angle to prove two triangles are similar. We only need two specific things. First, one angle in the first triangle must be exactly equal to one angle in the second triangle. Second, the two sides that sandwich or include those angles must be proportional, meaning they must share the same ratio. Let's look at the formal mathematical statement to see how this looks on paper. Suppose we are looking at triangle ABC and triangle DEF first. We identify our equal angles. We state that angle A equals angle D. This gives us our one pair of equal angles. Next, we look at the sides that form those angles. We need to check the ratio of the first pair of sides to the ratio of the second pair. We write this as side AB divided by side D equals side AC divided by side DF. As long as these two fractions result in the same value, the sides are proportional. If both of these conditions are met, the equal angle and the proportional sides, then we can conclude that triangle ABC is similar to triangle DEF. We use this tilde symbol to denote that they are similar. In the next slide, I'm going to break this down into a step-by-step process so you can see exactly how to apply this during a geometry problem. Breaking down the criterion. Now that we have seen the formal definition of Theorem 6.5, let's move on to the practical application. On this slide, I want to show you how to actually break down the criterion into a step-by-step process. To apply SAS similarity correctly, you can't just look at the triangles randomly. You must verify two specific conditions in a very precise order. Let's start with step 1, identify the angle. Your first task is to find one angle in the first triangle that is exactly equal to one angle in the second triangle. For the sake of our example, let's call these angle A and angle D. This is our anchor. It's the part of the triangle that stays the same in both shapes. Once you found that equal angle, move to step 2. Identify the including sides. This is a crucial part of the SAS name. You need to look specifically at the two sides that meet to form the angle you just identified in step 1. In our first triangle, triangle ABC, these would be sides AB and AC similarly. In our second triangle, triangle DEF, we are looking at sides DE and DF. Remember, the angle must be trapped between these sides. Next, we move to step 3. Check for proportionality. This is where we move from equality to ratios. You need to calculate the ratio of the corresponding sides. We check if the ratio of the first pair of sides equals the ratio of the second pair. Mathematically, we are checking if AB divided by DE equals AC divided by DF. If these two fractions result in the same value, then the condition for proportionality is satisfied. Finally, we reach our conclusion. If you have successfully completed both step 1 and step 3, meaning you have found an equal angle and confirmed the sides are in the same ratio. Then you have proven that triangle ABC is similar to triangle DEF. We use the tilde symbol to denote this similarity. Keep this process in mind, because in the next slide, we are going to see how this exact logic is used in a real-world scenario involving a digital projector. Real-world application, the digital projector. Now that we have mastered the theoretical steps of the SAS criterion, let's step away from the textbook and look at how this actually works in the real world. You might be surprised to learn that a common application of SAS similarity is found right in your classroom, the digital projector. Think about how a projector works. The lens creates an angle of light that projects an image onto a screen. To visualize this using the math we just discussed, let's set up a scenario. Imagine we have a small transparency slide, which we can think of as our first triangle, and then we have the large projected image on the wall, which represents our second triangle. Let's perform a step-by-step analysis using the 3 steps we learned in the previous slide. First, let's identify the angle. Just like we looked for the equal angle in our theorem, the angle at the projector lens is exactly the same for both the small slide and the large image on the wall. This means our vertex angle is equal. Second, let's look at the sides. We need to check the including sides. In this case, the distance from the lens to the slide and the distance from the lens to the wall act as our corresponding sides. These distances are proportional to the height and width of the image being projected. Third, let's check for proportionality. Suppose the projector is set to a scale of 10:1. This means every side of the image on the wall is exactly 10 times larger than the corresponding side on the slide. The ratio is consistent. Finally, we reach our result. Because we have verified that the angle is the same and the sides forming that angle are proportional, we can conclude that the image on the wall is a similar triangle to the image on the slide. This mathematical similarity is actually very important. It is exactly what ensures the image on the wall remains clear and is not distorted. However, be careful. As we will see in the next slide, if that angle were not perfectly aligned between those sides, the image would look stretched or warped. Common mistakes to avoid. First, let's talk about the non-included angle. This is arguably the most frequent mistake students make. Remember, for the SAS criterion to be valid, the angle you are looking at cannot just be any angle in the triangle. It must be the one trapped specifically between the 2 sides you are comparing. If you have 2 proportional sides but you pick an angle that isn't located between them, you cannot claim the triangles are similar. The angle must be the included angle. Second, be careful not to confuse equality with proportionality. In our previous lessons on SAS congruency, we looked for sides that were exactly equal, such as side AB equals side D. However, as we discussed in the earlier slides, similarity is about scale. Here, we are looking for a constant ratio, where the ratio of side AB to side D is equal to the ratio of side AC to side DF. Always ask yourself, am I looking for identical lengths, or am I looking for a consistent scale factor? Finally, pay close attention to your vertex correspondence. When you write your final similarity statement, the order of the letters matters immensely. If you have established that angle A is equal to angle D, then when you write the symbol for similarity, vertex A and vertex D must occupy the same position in the notation. For example, you should write delta ABC is similar to delta DEF. Rather than writing delta ABC is similar to delta DFE, if the letters don't line up correctly, your entire mathematical statement is technically incorrect. Now, before we wrap up our lesson with the final summary, I want to pause and discuss some common pitfalls. Even if you understand the theory, it is very easy to make small errors that lead to the wrong conclusion. Keep these 3 points in mind, and you will avoid the most common traps in similarity problems. Key takeaways. First, remember the core requirement. For SAS similarity to apply, you must have 1 pair of equal angles and 2 pairs of sides that are proportional. It is absolutely vital to remember that the angle you are looking at must be the included angle. As we discussed during our breakdown in the third slide, this means the angle must be the one trapped specifically between the two sides you are comparing. If the angle is elsewhere, the criterion fails. Next, I want to reinforce a distinction that often trips students up. Similarity is not the same as congruency. While we learned in previous grades that congruency means two triangles are identical in both shape and size, similarity only requires them to have the same shape. This means their angles are equal, but their side lengths can be different as long as they maintain that same ratio, just like the projector example we saw earlier. In terms of notation, when you are writing your proofs, we use the tilde symbol, which looks like a small wave to denote similarity. Finally, let's look at the mathematical condition one last time to ensure you can write it out correctly. To state that triangle ABC is similar to triangle DEF, you must show that angle A equals angle D, and that the ratio of side AB over DE equals the ratio of side AC over DF if these conditions are met. Then triangle ABC is similar to triangle DEF. All right, we have reached the end of our lesson, so let's take a moment to recap the key takeaways from today's session on the SAS Similarity Criterion. Make sure you review these points carefully before our next lesson. Great job today!